So, welcome to our 6-1 notes. A lot of this is review, but you should know these terms, and sometimes it's kind of easy to confuse what is what. So, Chapter 6, we're talking similarity, and in order to understand similarity, you need to understand ratios, rates, and proportions. Okay, so today we're going to talk about what those are and how we can work with them. So first off, a ratio. Okay, a ratio is just a comparison of two quantities. So this to that, right? You can write it as A to B, A colon B, or A over B, as long as you're not dividing by 0. Okay, so just this to that. The key thing with ratios is there is going to be either no units or the same units. So you're going to have like meters over meters, the meters cross off, or miles over miles, same units, they can cross off. So you can also write that as no units. Okay, so a ratio, I think we understand that. We've heard that term before. So there's this funny activity that someone did, I forget the name, but where they had discussed a mullet ratio. So, and here's a quick Google reminder if you forgot what a mullet is. We say that it's like a business in the front, party in the back, right? These are all mullets, right? But you can see that some have a little bit more party in the back than others. And so, actually, trying to give credit here. This was done by a teacher named Matt Vaudry, and so he came up with this idea just how there's different mullet ratios that we can create. The ratio would be the ratio of party in the back to business in the front. Okay, we're not going to do that lesson for time's sake, but I just want to give credit where credit is due. So let's say our mullet ratio of party to business is 2 to 1. So that means the length of the party in the back is going to be double the length of the business in the front. Right? So you can draw a little mullet for Adobe. For example, let's say this is, I don't know, like 2 centimeters, and this is 4 centimeters. Right, so we can write the length of this party in the back is 4, the business in the front is 2, so you can write that as 4 centimeters over 2 centimeters, and it's 2 to 1 ratio, so that matches what we are looking for. But the key thing, one of the key things I want to point out to you is that a ratio, of course, could be a different fraction with the same simplification. So if I change this to, let's see, he grows his hair out, as long as we double everything, right? So if this was 4 centimeters, this would have to be 8 centimeters, right? 8 centimeter party, 4 centimeter business, and it's the same. 8 to 4 is the same as 4 to 2 is the same as 2 to 1. So you can play around with this 9 to 1. But another key thing I want to point out is if you have a ratio of 1. Again, just like this one, you could write 1 as, for example, 2 to 2. It could be 4 to 4. It could be 0.5 to 0.5. And again, a ratio, we don't have to have units because if I write centimeter over centimeter, that just crosses off, right? So we don't have to have any units at all. So like, 0.5 business party over 0.5 business, right? That could be like a 1 to 1 ratio, or like for example, if it was 2 and 2, that could be a 1 to 1, or 4 to 4. I mean, you can play around with it, but it basically just means that the business in the front and the party in the back have to be the same ratio. Okay, so that's a ratio. The key thing: no units or same units. Now, a rate is very similar. It's the same thing. It's a comparison of two numbers by division. However, the key thing is the units are different. So like miles per hour, or feet per second, or people per year. Anything where you have two different things, that's called a rate, not a ratio. Right? 15 miles per hour. Just like with ratios, though, we can take them. We can say, okay, 15 miles per hour. We can multiply both of those by 2, because 2 over 2 is just an equivalent form of 1. Right, 15 miles per 1 hour is the same rate as 30 miles for 2 hours. And again, I can multiply numerator and denominator. Well, actually, I could take this one, actually, just multiply both by 3. Right, that would be the same as 45 miles in 3 hours. Right, same thing. If I take 15 miles in every 1 hour, I multiply, let's see, what do I need to multiply? I need to multiply by 10 to get to this one. So I multiply this one also by 10, right? Multiply by 10, right? Because 10 over 10 is just 1, you're not changing the number. 15 times 10, 1 times 10. So all of these are the same rate, 30 miles for every 2 hours, 45 miles every 3 hours, 150 miles every 10 hours. Okay, so rates and ratios, the key thing is units are different, or there's no units here, or the same units. Okay, so we could practice this in real life. We can apply this by whenever we go shopping. Oftentimes stores sell different amounts, and by calculating the rate or ratio, we can see which is the best deal. Okay, so I could find the unit rate, which is the price per 1 can for a can of Coke. By calculating that, I could see who is what is the best deal for me. So let's take a 6-pack selling for $3, right? A 6-pack selling for $3. That means my $3, right? I'm going to write a rate here. My $3 will buy me 6 cans. Okay, $3 for 6 cans. Now I want to reduce this. I want to find the price for just 1 can, right? That's the unit rate. So I want to work with this fraction. I want to say, okay, I want to divide this by 6. Divide this by 6, right? 6 divided by 6 makes 1. But you can't just divide the denominator by 6. That would change the fraction. But if you think about it, if you divide both of these, numerator and denominator, by 6, you're dividing by 6 over 6, which is just 1, right? You can divide by 1, and it's not going to change the number. So we see that 3 divided by 6, that's going to give me half a dollar, or 50 cents. Okay, so if they're selling a 6-pack for $3, you know, I think we know that intuitively, but working with it in terms of rates, we can say it's 50 cents for 1 can. All right, why don't you go ahead and pause the video, see if you can figure out which is the best deal. Okay, so hopefully you pause the video. I'll just work these out really quickly. So if I take $4 for 12 cans, divide by 1, right? This is just 1. 12 over 12 is just 1. I'm going to get, of course, 33. So 4 divided by 12 is 1/3, or 33 cents for 1 can. And finally, a 24-pack selling for $9. So $24 buys me, $9 buys me 24 cans. I want to turn that into 1 can, so I want to divide by 24 over 24, right? That's just an equivalent form of 1. So over here we get 1 can, and we have to find out what 9 divided by 24 is. Let me just go ahead and take out my calculator here. 9 divided by 24. Okay, 0.375. So since it's money, we'll round that up to 38 cents. So actually, despite what you might think, this one was the cheapest price. Okay, rates and ratios. This is the unit rate. We divided by an equivalent form of 1 to find out which is the cheapest. Let's go ahead and see if you can do the same thing here. So I've got some peanut butter. This is actually photos that I took at Target a few years ago. The prices are probably a little bit different. So I want to find the unit rate, the price per 1 ounce. Okay, it might be hard for you to read this. This is 16.3 ounces here. And it says 2 for $5. You can just go with a $2.50 price. This is $5.74. It's kind of hard to see that. That's 40 ounces. And this is 64 ounces, selling for $8.79. Okay, these are actual prices, however many years ago that I took these at. So go ahead and pause the video, see if you can tell me what is the best price per ounce. Okay, so if you didn't know where to start, here's my hint to you. I want to calculate the unit rate, the price per 1 ounce. So I start off with this rate, this many dollars per this many ounces, reduce them all and compare, please. Okay, let's go ahead and check it out. Okay, so here are the final results. We divide by equivalent forms of 1 for all of these. 15 cents per ounce here, so you have to pay 15 cents to get an ounce here. You have to pay about 14 cents per ounce here, and you have to pay about 14 cents per ounce here. Now this one's actually cheaper because you're rounding up here. So this is the actual cheapest, but if you think about it, these are quite similar, so maybe you think to yourself, since they're both 14 cents, if I round it, maybe I'm just going to go with this one. But in any case, now you can use rates, unit rates, to calculate which is the best deal. Okay, so we talked about rates with units, we talked about ratios where there's no units. Let's finally finish this out by talking proportions. So a proportion, as you've studied before, is a statement that says that two ratios or rates, so again there could be no units, same units, or different units like miles per hour equals miles per hour, or meters over meters equals meters over meters, or no units. But we've seen this before, but it's basically just saying, hey, this ratio is the same as this ratio, right? 1 to 2 is the same as 2 to 4, or this rate is equal to this rate. Like 15 miles for 1 hour is the same rate as 30 miles for 2 hours. You can also write it as this to this equals this to this. You can also say it as A to B is the same as C to D. So if I have like something like an x here, and I want to solve for this x, you've probably done this before, but how do we solve? Well, there's actually a way that you've done before called cross multiplication. Right? That's the kind of quick way. But really, how does cross multiplication work? Is if you think about it, when I'm dividing by fractions, an easy way to work with that is if I'm dividing by b, what I could do is just multiply both sides by b. I'm trying to show this down here as well, but I'll just do it again. When you multiply both sides by b, you get b over b here, and that crosses off. And then you would want to multiply both sides by d to get rid of that. So if I multiply both sides by b and then multiply both sides by d, so where am I here? I have a equals x over d times b, right? So I've gotten rid of the b from down there. If I multiply both sides by d, right, d over d makes a 1. So I'm left with a times d equals x times b, right? A, or whatever, C, I guess it was originally c here. So in other words, when I'm doing this, when I do cross multiplication, you may have even drawn it like this before. When you're trying to solve for something, you can just go like this, and you can say a times d equals c times b. But I just wanted to reiterate, that's not magic. All you're doing is you're doing this in one step, where here you're doing it in 2 steps, right? You're multiplying both sides by b, that crosses off. Then you're multiplying both sides by d, that crosses off. So it just saves you a step. You kind of just go this times this equals this times this. It's not magic though, it's just, it's just 2 steps shortened into 1. Okay, so again, if I know that either the rates or the ratios are equal, right, they have to be equal, you can solve for missing values using a proportion. Okay, so let's say that I know that this dopey 1 and this dopey 2 form a proportion. Like their mullet ratio of party to business is the same, right? Equal ratios. How long would the party in the back have to be? This is just kind of obvious, but let's say I have a 2 to 2 ratio here, right? 2 to 2 is a ratio of 1, right? Or 1 to 1. You can write it as 1 to 1. If I know they must be the same, and this is 11 inches, well then obviously I know that this must also have to be 11 inches, right? Because 2 to 2 is the same as 1, which is the same as 11 to 11. So oftentimes you're just trying to fill in what is this missing part here, right? If you know these must be the same ratios, you can always solve for this missing piece. Sometimes you do it in your head, but other times, we need a little bit of algebra here. Okay, so let's move on and talk about our last examples. Another kind of relevant one is, since I know like soda, for example, is going to be the same amount of calories no matter how small or how big, I can apply proportions to solve for how much would be in here. Let's say it's someone pours it out of the can into a cup, and so I can't look at the nutrition information, but I know my proportions. I know, let's say I know a regular can, 12 ounces of root beer has 180 calories. How many calories would be in a mini size? Okay, so why don't you go ahead and just pause and try to calculate that. How many calories would be in a mini size root beer, right? It's obviously going to be less because that was 12 ounces. This is 8. Go ahead and set up a proportion. This to this must be the same as this to this, and then solve. Okay, if you're stuck, right, so don't pause the video if you're still going, but if you're stuck, we could say something like, okay, I know that there is 180 calories in 12 ounces of root beer, right? And I know because it's the same root beer, right? If it's a smaller can, 8 ounces, I want to line that up with this, okay? And I'm going to say, I'm trying to figure out how many calories are in this mini one, so I'm going to say X calories, okay? So in other words, this to this is the same as this to this. This rate must be equal to this rate. And now I'm just going to solve for this. So again, pause the video and go ahead and solve for how many calories. Okay, so again, we could do this in 2 steps. I've got the 12 and the 8 down here. I can multiply both sides by 12. That would clear this out. And then multiply both sides by 8. That would clear this out. 2 steps. Or it's a little bit easier just to cross multiply. So we do it in 1 step. Okay, so let's go ahead and calculate. So we get 12x. I'm going to drop the units just to make it easy. Equals 180 times 8. 180 times 8, which is 1,440. Okay. Now, to solve, we can just divide by 12 on both sides. 12 over 12 makes 1. So x equals, well, 144 divided by 12 is just 12, right? And then I have an extra 0 here, so that's 120 calories. Okay. Now, this is a rate, calories per ounce, calories per ounce. You could also do ratios where there's no units. If it was a 2-liter bottle, though, we'd have a little bit more problems. So if I had 180 calories, I know there's 180 calories in a regular 12-ounce can. I can't just put 1 liter here. I have to convert a liter to an ounce. I have to convert a liter to an ounce. In fact, I have 2 liters here. So let's go ahead and pause for a second. All right, so I'm trying to figure out, okay, I've got 2 liters, and I want to convert this so that to ounces, just so it'll play nicely, right? So we have a nice rate here. So this is 2 liters. I could use a kind of some math to figure it out, but because of time's sake, we'll just ask our friend Google. 2 liters equals how many ounces? And Google is so nice for us, we can just type it in. 2 liters to ounces, and that tells us about 67.628 ounces. 67.628. So let's go ahead and write that down. 67.628. Okay. So now this is a nice rate. Everything calories per ounce. Calories per ounce. Okay, we're trying to find this x. Again, I can multiply both sides by 12. Multiply both sides by 67. That would be 2 steps. So we'll cross multiply and we can do it in 1. So we get 12x equals 180 times 67.628. 180 times 67.628, and that is 12,173.04. I'm just going to divide that by 12 to finish off the problem. Divided by 12, and we see that in 1 2-liter bottle, which I probably drank one of those myself at one point in my life, has over 1,000 calories. That's more than half the calories we need for the whole day, including food. So that is pretty intense. So if we're going to drink soda, it might be best to go with this guy here. All right, last one. Again, proportions just mean that the rate or the ratio is the same. So if I'm going to enlarge something, right, or shrink something down, as long as it's done proportionally, right, you didn't stretch one way or the other, you can still solve for the missing length. So let's say I took a Mona Lisa and I blew it up, but it was proportionally, so I can still make a nice ratio. This would be a ratio because everything's in centimeters. The units are the same. So go ahead and find what is the length of the original painting. What is this right here? Okay. Try and pause and solve it without my help. I'll put a hint up in a few seconds, so go ahead and pause and try it. Okay, so if you're stuck, again, we can set it up as 77 centimeters to x centimeters. Right, that's this guy. Is the same as 140 centimeters is to 100 centimeters, right? This to this equals this to this. Okay. Now the interesting thing about proportions, though, is that it doesn't actually. So if we cross multiply, actually, let's just go ahead and cross multiply here. We would get 140 times x equals 77 times 100, so that's 7700. Okay. But let's say you didn't do it that way. What if I did this? 77 to 140. I'm going to drop the units because we don't actually need units, right? We don't need units, it's a ratio. 77 to 140, would that be the same as this is to this? X is to 100. Let's see if this produces the same thing. If I cross multiply, notice I get 7700 equals 140x, right? If I cross multiply, look, it was the exact same thing. So as long as I'm consistent with it, right, I could go this to this equals this to this. I could match up this to this equals this to this, right, because it blew up proportionally. I just can't be inconsistent. I can't be like 77 goes to 100 and x goes to 140. That wouldn't work. But as long as I'm lining things up, everything is cool. I can solve by dividing by 140 on both sides. And so our final answer, 7700 divided by 140 is 55. 55. 55. Always include our units here, right? Everything was in centimeters, so this must be in centimeters. So x equals 55 centimeters. All right, so let's finish by turning to our vocabulary sheet very quickly and just write down what we've talked about. So our vocab, first off, again, a ratio is a comparison between two values. You write them like this. We want to try to simplify them when possible. Again, ratio is going to have the same units or no units, right? Because those units can cancel out, same units or no units. So the width of this compared to the length of this, 14 feet to 7 feet is fine, or 7 to 14, excuse me. I can just cross off these. I can write 7 to 14 and 1 to 2. Right, 64 meters to 6 meters simplifies to 32 to 3, right? Same units or no units. Again, if I have different units, that's called a rate. Right? A proportion is an equation that states that two ratios or rates are equal. Right? This to this is the same as this to this. Maybe I blew it up or shrunk it down, but that's what we're dealing with this chapter. And again, we saw how you can either write it like this to this, 10 to 20 is the same as 15 to 30. You could be like 10 to 15 is the same as 20 to 30. You could kind of go backwards, say 15 to 10 is the same as 30 to 20. It's all the same. And so let's finalize that by turning to our next page, the properties and theorems. Again, the cross product property is just saying that if I've got a proportion, so this to this is the same as this to this, I could do it in two steps. I can multiply both sides by b, right? Then I can multiply both sides by d, and I'm left with a times d equals c times b, right? I could do it in two steps, or I could just kind of go like this equals this, right? The cross product property is just saying in one step I can do that, okay? Finally, additional properties. If you've got a proportion, like if a to b is the same as c to d, I can turn it on its head. For example, b to a will be the same as d to c, right? If a to b is the same as c to d, I could also go across a to c, must be the same as b is to d, right? That's just kind of like doing what I was doing with this here, right? If I go this to this, the same as this to this, I could say backwards that this to this is the same as this to this, so on and so forth. It's all the same fraction. Finally, if a to b is the same as c to d, if I want to add something to this, then I could say something like this. If I'm going to add something, I could say a plus b over b. A plus b over b would be the same as, think about what's b over b. If I'm adding b over b, that's just 1. So what would be 1 over here? Since d is my denominator, it would not be b over d. I'm not adding b on this side. It's going to be d, right? Because b over b is 1 over here, d over d is 1 over here. So this is just another, just kind of other ways you can write proportions. Okay, that concludes our notes for 6-1.